In this class, we are going to learn some of the algebraic properties of tensors. The first one is the linear combination of tensors. The sum or difference of two tensors of the same rank and type is another tensor of the same order and type. So what do you mean by linear combination? It can be either a sum or difference. The sum or difference of two tensors of the same rank and type is another tensor of the same order and type. In the previous classes, we have seen the different type of tensors, contravariant and covariant, and also how to define the rank of a tensor. So here we are discussing the algebraic properties of tensor, and the first property is regarding the linear combination of tensors, and it says that sum or difference of two tensors of the same rank and type is another tensor of the same order and type. Now let's see the proof of this statement. Let A alpha beta and B alpha beta be two tensors of the same order and type. Okay. Then their components in the coordinate system x prime mu will be A prime alpha beta and B prime alpha beta, right? So I can write A prime alpha beta is equal to partial derivative of x mu with respect to x prime alpha, partial derivative of x mu with respect to x prime beta, A mu nu. So this is the transformation for a covariant tensor of rank 2. Now B prime alpha beta can be written as partial derivative of x mu with respect to x prime alpha, right? Partial derivative of x mu with respect to x prime beta, B mu nu. Okay. Then I can define C prime alpha beta is equal to partial derivative of x mu with respect to x prime alpha, x nu with respect to x prime beta, C mu nu. Okay. And if I add A prime alpha beta and B prime alpha beta, if I add these two, I will get A prime alpha beta plus B prime alpha beta is equal to partial derivative of x mu with respect to x prime alpha, partial derivative of x nu with respect to x prime beta, A mu nu plus partial derivative of x mu with respect to x prime alpha, partial derivative of x nu with respect to x prime beta, B mu nu. But here we can see that I can take out the common. Okay, so if I take out partial derivative of x mu with respect to x prime alpha and partial derivative of x nu with respect to x prime beta, then I'll get a mu nu plus b mu nu, right? So it can be plus or minus. I am discussing about the linear combination of tensor, which means sum or difference. So I can either add them or subtract them, right? Then I can write partial derivative of x mu, x alpha, x nu with respect to x prime beta. This can be c mu nu, right? Then if you see the definition of c prime alpha beta, then this can be written as c prime alpha beta, because it is similar to the right hand side of c prime alpha beta, which means a prime alpha beta plus or minus b prime alpha beta, you get c prime alpha beta, right? So this is the proof for the addition or the linear combination of tensors. That is, the sum or difference of two tensors of the same rank and type is another tensor of the same order and type. The next property is the symmetry or antisymmetry of tensors. Symmetry or antisymmetry of tensors. An important property of a tensor is its symmetry or non-symmetry with respect to an interchange of some of its indices. When the relative position of two indices, okay, either contravariant or covariant, is immaterial, then the tensor is called symmetric tensor respect to these two indices. Okay, so mixed tensor is not allowed only if the relative position of two indices, that is, it should be either contravariant or covariant, and if that relative position is immaterial, then the tensor is called symmetric tensor. Okay, for example, I take s mu nu. Okay, so if the relative position of these two indices is immaterial, that is, even if I interchange the indices, so if I interchange the indices, then I get s nu mu. Okay, so when the relative position of the two indices is immaterial, which means that even after interchanging these two indices, they are the same. Okay, then this tensor is called symmetric tensor. That is, when the relative position of two indices of a tensor is interchanged and the tensor obtained is same as the original tensor, then the tensor is called symmetric with respect to those indices. When the relative position of two indices of a tensor is interchanged and the tensor obtained is same as that of the original tensor, then the tensor is called symmetric with respect to those indices. Symmetric with respect to those indices. Okay. For example, consider S mu nu, and if you interchange mu and nu, you get S nu mu, and if it is equal to S mu nu, then it is a symmetric tensor. Okay. And similarly, you also have antisymmetric tensor, that is when the relative position of the two indices of a tensor is interchanged and the tensor obtained differs only in sign from the original one. Then the tensor is called skew symmetric or antisymmetric with respect to these two indices. That is, suppose if I have a mu nu, okay, then if I interchange mu and nu, I will get a nu mu. But if this is equal to the negative of the other, then this tensor is called skew symmetric or antisymmetric with respect to these two indices. Okay. When the relative position of two indices of a tensor is interchanged and the tensor obtained differs only in sign from the original one, then the tensor is called skew symmetric or antisymmetric with respect to those indices. Okay, so either the tensor has to be a covariant tensor or it has to be contravariant tensor. You cannot define the symmetric property or antisymmetric property for a mixed tensor. Okay, this is not possible. And also there is one important property that you have to note, that symmetry or antisymmetry properties of tensors are preserved under coordinate transformation. For instance, we have seen that S mu nu is a symmetric tensor and A mu nu is a antisymmetric tensor. Then in another coordinate system, okay, so when I do the transformation, this will be S prime alpha beta. This can be A prime alpha beta, right? So in another coordinate system, you can see that S prime will be symmetric and A prime will remain antisymmetric respectively in all other systems of coordinates. Okay, that is a property of tensor. The symmetry or antisymmetry properties of tensors are preserved under coordinate transformation. Okay. And similarly, from any covariant tensor T mu nu, okay, which is of order 2, one can construct its symmetric and antisymmetric part. So any covariant tensor can be written in terms of its symmetric and antisymmetric part. So the tensor S mu nu and A mu nu are uniquely determined as S mu nu is equal to half of T mu nu plus T nu mu, and the antisymmetric tensor can be written as half T mu nu minus T nu mu. also there is a notation which is much more convenient. That is, the rank 2 symmetric and skew symmetric tensors are usually denoted as S mu nu with a ordinary bracket, and the antisymmetric A mu nu is denoted by a square bracket. Okay, so if you have a round bracket, then it is symmetric, and if you have square bracket and some indices are within the square bracket, then it means that those indices are antisymmetric with respect to each other. Okay, the construction of symmetric and skew symmetric tensors from a second order tensor that we have described above can be generalized to higher order tensor as well. Okay, this is for second order. Similarly, I can also write for third order tensor T alpha beta gamma. Okay, so one can construct a completely symmetric tensor which is given by 1 by 3 factorial T alpha beta gamma. Okay, so this is symmetric, completely symmetric tensor. Therefore, I denote it by a round bracket. That is, this tensor is symmetric with respect to all these three indices, alpha, beta, and gamma. So this is given by 1 by 3 factorial T alpha beta gamma plus T gamma alpha beta plus T beta gamma alpha plus T gamma beta alpha plus T alpha gamma beta. Okay, so this tensor is completely symmetric under interchange of any two of its three indices. One can also construct a completely skew symmetric tensor, okay, or the antisymmetric tensor T alpha beta gamma, which is given by 1 by 3 factorial T alpha beta gamma plus T gamma alpha beta plus T beta gamma alpha minus T beta alpha gamma minus T gamma beta alpha and minus T alpha gamma beta. Okay, so the tensor is completely antisymmetric under interchange of any of its three indices. Okay, fine. Now we move on to the Kronecker delta. That is, here we introduce an important tensor, that is a mixed tensor of rank 2. A mixed tensor of rank 2 whose components in a coordinate system are defined as A mu nu is equal to 1 for mu is equal to nu and it is equal to 0 for mu not equal to nu. Okay, and A mu nu can have a transformation to another coordinate system which is given by A prime mu nu is equal to partial derivative of x prime mu with respect to x alpha, x beta with respect to x prime nu, A alpha beta. Okay, But here we know that this A alpha beta will survive only if alpha is equal to beta. That is the property of Kronecker tensor, right? Therefore, if I put alpha equal to beta, then this becomes x prime nu, which has exactly the same value as that attributed to the components A mu nu. Okay. Thus, the mixed tensor possesses a remarkable property that the values of its components are defined once and for all for every system of coordinates. So we denote this tensor by a symbol delta mu nu, which is the Kronecker tensor. Okay, the Kronecker tensor, and we refer to it as the fundamental mixed tensor. Okay, it is the fundamental mixed tensor. It may also be mentioned that this delta mu nu is the only tensor of rank 2 which is symmetric in its indices, though one of them is contravariant and the other is covariant. Okay. Now we'll see a problem. Show that Kronecker tensor is a rank 2 tensor. Show that Kronecker tensor is a rank 2 tensor. So we know that the Kronecker tensor delta mu nu is defined as partial derivative of x mu with respect to x nu. Okay. Therefore, the transformation delta prime mu nu can be written as partial derivative of x prime mu with respect to partial derivative of x prime nu, right? Now I can multiply partial derivative of x prime mu by x alpha and x beta x prime nu, right? And I also multiply this by gamma and gamma. Now I can rearrange x prime mu with respect to x alpha, then x gamma with respect to x prime nu, and x beta with respect to x gamma. Okay, and this I can write delta function of beta and gamma, and now you can see that it transforms in this manner. Okay, so delta prime mu nu transforms to delta beta gamma in this manner. That is, mu transforms in a contravariant way and nu transforms in a covariant way, right? So here alpha is equal to beta, and therefore here also alpha is equal to beta. Therefore I can write x prime mu with respect to x alpha, x gamma with respect to x prime nu, delta alpha gamma. Okay, so delta prime mu nu transforms to delta alpha gamma in this way, in this manner. Okay, that is one contravariant and one covariant. So this shows that the Kronecker tensor is transforming as a mixed tensor of rank 2 under the transformation law. Thus, it is a mixed tensor of rank 2. Okay. The next topic is the generalization of Kronecker tensor. Generalization of Kronecker tensor. Okay. So here this is a Kronecker tensor of rank 2. Okay. Similarly, I can define a Kronecker tensor of rank 4. Delta alpha beta and mu nu. So this can be written as determinant of delta alpha mu, delta beta mu, alpha nu, beta nu. So Kronecker tensor of rank 4 can be written in terms of Kronecker tensor of rank 2. Okay, and you can have only Kronecker tensor with even rank. With odd rank you cannot have, because if you have one covariant index, then correspondingly you should have another contravariant index. Therefore, it appears only in the even number of ranks. So after the fourth order Kronecker delta, we have the sixth order Kronecker delta. Okay, that is delta alpha beta gamma mu nu rho is equal to, this can be written in terms of the second order Kronecker delta function, sorry, Kronecker tensor, right? So the sixth order or the rank 6 Kronecker tensor can be written in terms of the Kronecker tensor of rank 2, delta alpha mu, delta beta mu, delta gamma mu. Delta beta nu, right? No, delta alpha nu, delta beta nu, delta gamma nu. Similarly, delta alpha rho, delta beta rho, delta gamma rho. Then this is of rank 6, right, or 6th order. Now Kronecker tensor of 8th order of rank 8, delta alpha beta gamma delta mu nu rho sigma. Okay, this can be written as delta alpha mu, delta beta mu, delta gamma mu, delta delta mu. Delta alpha nu, then delta beta nu, delta gamma nu, delta delta nu. Then delta alpha rho, delta beta rho, delta gamma rho delta delta rho, delta alpha sigma delta beta sigma delta gamma sigma delta delta sigma, right? So these are the generalization of Kronecker tensor in terms of the second order Kronecker tensor. Now we have to define two important properties of tensor. One is the outer product of tensors and another one is the contraction of tensors. So first we will see the outer product of tensor. So what do you mean by outer product? For example, if you have a tensor A alpha beta, okay, which is a contravariant tensor of rank 2, and you have another tensor B mu nu, which is a covariant tensor of rank 2, then their product, okay, will be a tensor C alpha beta mu nu, okay, which is of the order 4, okay, such that what will be the transformation? That also you have to write. Suppose if A alpha beta will transform as A prime alpha beta is equal to partial derivative of x prime alpha with respect to x delta and partial derivative of x prime beta with respect to x sigma A delta sigma, sorry, here it has to be A alpha beta, okay, A delta sigma. And if B mu nu transforms like B prime mu nu is equal to partial derivative of x lambda with respect to x prime mu, x rho with respect to x prime nu, B lambda rho. Then their outer product C prime alpha beta mu nu will be, I have to take the outer product of the right hand side, that is partial derivative of x prime alpha with respect to x delta, x prime beta with respect to x sigma, right? Then partial derivative of x lambda with respect to prime mu, x rho with respect to prime nu, A delta sigma and B lambda rho. Okay. Then we know that the outer product of A and B is C. Therefore, I can write x prime alpha with respect to x delta, x prime beta with respect to x sigma, x lambda with respect to x prime mu, x rho with respect to x prime nu, A multiplied B will be C delta sigma lambda rho. And you can see that they transform. Okay, so this is the transformation of a mixed tensor of rank 4. This is the transformation for a mixed tensor of rank 4. Okay, so if you take the outer product of two tensors, one contravariant of rank 2, another covariant of rank 2, then the result is a mixed tensor of rank 4. Okay, so such product are called outer product of tensors, where the rank is increasing by 2. So initially I started with rank 2 tensor and finally I got a rank 4 tensor. That is, the rank of the tensor increased by 2, right? So such product are called outer product of tensors. And the next important property is the contraction of tensors. Contraction of tensors. So what is meant by contraction? For that, first I will define a mixed tensor A, alpha, beta, gamma, delta. Okay, a mixed tensor of rank 4. And by the law of transformation, I have A prime alpha, beta, gamma, delta is equal to partial derivative of x prime alpha with respect to x mu, partial derivative of x prime beta with respect to x sigma, and partial derivative of x prime gamma with respect to x lambda, partial derivative of x rho with respect to x prime delta, A mu sigma lambda rho. Okay. Now I define an operation called contraction. So what is contraction? It is an operation where we put one of the contravariant index equal to one of the covariant index. Okay. So contraction is an operation where we put one of the contravariant index equal to one of the covariant index. Okay. For example, here if I can take delta equal to alpha, right? So for example, I can take here delta is equal to alpha, so that this become A prime alpha beta gamma. Now if delta is alpha, here also I will have alpha. Then on the right hand side also I have to make the same correction, which means on the right hand side if I put delta equal to alpha, then here there is alpha, here there is delta, so both will become alpha. So I can write partial derivative of x prime alpha with respect to x mu, x prime beta with respect to x sigma, x prime gamma with respect to x lambda, x rho with respect to x prime alpha, A mu sigma lambda rho. See, all the other things are as it is. Instead of delta, I just substituted alpha. Okay. So in that case, the x prime alpha and x prime alpha will be cancelling. So I have partial x prime beta with respect to sigma, x prime gamma with respect to x lambda, and x rho with respect to x mu. Okay, this and this. And A mu sigma lambda rho. Fine. Now, this is nothing but the Kronecker tensor that we have defined, right? So this can be written as partial derivative of x prime beta, x sigma, x prime gamma with respect to x lambda, delta rho mu, A mu sigma lambda rho. So this will survive only if rho equal to mu, otherwise it is 0. Therefore I have to put rho equal to mu. So I get x prime beta with respect to x sigma, x prime gamma with respect to x lambda and a mu sigma rho rho. So instead of lambda, I have substituted rho. Okay. So thus, you can see that here it will be a prime alpha beta gamma alpha is equal to this one, right? So this shows that a prime alpha beta gamma alpha is a tensor of rank 2. This is a rank 2 tensor. So initially I started with a rank 4 tensor, right? And I have done the contraction delta equal to alpha, and finally I have got a tensor of rank 2. Okay, so the process of getting a tensor of lower order, that is reduced by 2, by putting a contravariant index equal to a covariant index and then performing the summation indicated is known as contraction. Okay, so what is contraction? Contraction is the process of getting a tensor, of lower order, okay, not simply lower order, which is reduced by 2. The rank is reduced by 2 by putting a contravariant index equal to a covariant index and performing the summation. This is called contraction. Okay, so the tensors A, alpha, beta, gamma, alpha, okay, this is one contraction. I can also put beta equal to delta here. So you can put any one contravariant index equal to the covariant index. So instead of alpha equal to delta, I can also put beta equal to delta. If I put beta equal to delta, then I will get, then I will get a alpha, beta, gamma, beta, right? So here it is a alpha, beta, gamma, alpha. If I put beta equal to delta, then I'll get a alpha, beta, gamma, beta, right? If I put gamma equal to delta, I will get a alpha, beta, gamma, gamma. Okay, so you can obtain more than one tensor from the contraction of the same tensor. Okay, and all of them are different from each other unless this tensor A alpha, beta, gamma, delta is symmetric with respect to alpha and beta. Okay, so this is one property, contraction of tensors. So we have defined outer product of tensors. Now there is something called as inner product of tensors. Now let's see inner product of tensors. Okay, so to take the inner product of two tensors, first you have to perform their outer product, okay, and then do the contraction. That is known as the inner product of two tensor. That is, given A alpha, beta, gamma and B mu sigma lambda, if I want to take the inner product of these two tensors, then the first step is to form their outer product. Form their outer product, because outer product we have already defined how to take the outer product. So to take the inner product, first step is to form their outer product. Okay, and then we have also defined what is contraction, and the second step is to contract this outer product by putting one covariant index equal to contravariant index, and the result is called as the inner product. Okay, so here if you see, these are two tensors, A alpha beta gamma, B mu sigma lambda. If I take the outer product, then I'll get A alpha beta gamma, B mu sigma lambda. Okay, so this is the outer product. If I contract this by putting mu is equal to gamma, then the result is A alpha beta gamma, B gamma sigma delta. Okay, so this is also a tensor called as the inner product of the given tensors. So this is the inner product of the given tensors. First step is to take the outer product and then contract. So the inner product of two tensors is obtained by first taking their outer product and then by contracting it. Okay, so we can get several inner products for the same two tensors, because contraction can done in different ways. Okay, so once you take the outer product, then I can contract using mu equal to gamma or alpha equal to sigma, beta equal to lambda. There are many ways of contracting. So depending upon the which contraction are you preferring, there will be different inner product of the given tensors. Therefore, we can get several inner product for the same two tensor by contracting in different ways. Fine. So today we'll stop here.